So now we're going to go ahead and actually apply parametric equations to a couple of problems that we may see. This first one is finding the parametric equation or the parametrization of a line or a line segment. So they're asking us to find the parametric equation for a line segment, or sorry, for a line that passes through both points A and B. So, boop, that line right there. Now, we don't know what this line or what the equation for this line is, but we do know a couple of other things. First of all, we know that point A is going to be -2, 3, and point B is going to be 3, 6. And we can actually use vectors to try and solve this equation right here. So let's go ahead and draw two vectors. The first one is going to be from the origin to my A, and the second one is going to be from A to B. Let's make these a little bit thicker. So we have these two vectors, and we're also going to need one more point. So on this line, anywhere on this line, I'm going to go ahead and put an arbitrary point, and I'm going to call it P for point. So let's say it's that point right there. I'm going to call that point P, and this is just going to have some X and Y value. I don't know exactly what it's going to be, but I do know a couple of things. First of all, I know that this right here, vector AP, is a scalar of AB. In other words, if I were to take A and B and I were to stretch this vector out in some way, I would make it longer or shorter, doesn't really matter. It would eventually reach point P. So it's a scalar vector. In other words, it's going in the same direction. So let's write down a couple of things that we know. First of all, we have vector, we're going to need one more vector. And that vector is going to be vector OP, which is going to be the vector from the origin all the way to point P. So let's use logic to figure out exactly what we know. First of all, we know that vector OP is equivalent to vector OA plus vector AP. In other words, going straight from here to here is the same thing as going here to here and then here to here. That's what that means. Now, the other thing that we know is that OP is the same as OA times this right here. But we know that AP, vector AP, this one right here, is the same thing as a scalar of vector AB. So in other words, we're adding a value by which we're multiplying AB. We don't know what that value is, so we're going to call it T. And that would actually make vector AP, right? If we take AB, which is this right here, and we multiply it by some value to make it longer, we don't know what it is yet, but that's okay. It would be equivalent to this whole thing, this vector AP. So that's what that's saying right there. Now, to find the parametrization of this equation, remember, a parametrization is going to be the same as basically a vector. So we're going to be looking for x to be equal to something and y to be equal to something. Now, let's go ahead and put in a couple of points that we know, right? So we have vector OP, we don't know what that is, so we're going to leave that as x comma y. But we know that OA, O to A, is -2 comma 3. And we know that we have to add this to some scale of this vector right here. And so this vector right here, AB, it's not a vector in standard form. So we have to go ahead and make it into standard form by using our head minus tail rule. So if this is the head, we're going to subtract the tail. So we're going to take 3 minus a -2, comma 6 minus 3. So now we can actually go ahead and solve this, and we have the same thing, you know, OP, we still don't know what that is. We're looking for this vector right here, O to P. But we do have this -2 comma 3, which is vector OA, that one right there. And we are adding it to T times 3 minus -2 gives us 5, and 6 minus 3 gives us 3. So now we can actually go ahead and add these two vectors together. First and foremost, we're going to need to distribute this t into here, which is not a problem. It's just 5t and 3t. And then we simply add them together. So we have -2 plus 5t. So x comma y is equal to -2 plus t times 5. And then 3 plus t times 3. So we can go ahead and write that in. -2 times, plus 5t, comma 3 plus 3t. And so if you notice, now we actually have a parametrization of this value because this vector is what we're looking for. And since that vector has an x and a y value, and that x and y value happen to be -2 comma 5t, and this happens to be 3 plus 3t, then it would make sense that this vector right here is our parametrization of any single point on this line. So let's talk about what that means. We're not necessarily looking for this line right here. That's not what we're doing. What we're looking for is the fact that this line right here, let's do it in green. What we're doing is we are figuring out the fact that this line right here, this vector OP, could point to any single point on this line, and it won't matter what point I choose. So I could have chosen that point right there, and that is still going to be a scalar of AB. I could have chosen that point right there, but the fact of the matter is that this vector is going to point to any point on this line, provided that my t is the scalar of whatever that point is. And when we graph it into a calculator, it's going to basically generate every single point, and so it's not going to matter. And to prove this to you guys, we're going to go ahead and show you what happens if you plug in a value into this right here. For example, let's say I plugged in the value 0. So t is equal to 0. So when t is equal to 0, that means I have -2 plus 5 times 0, comma, 3 plus 3 times 0. And so when t is equal to 0, this cancels out, and I get -2 comma 3. So that means that this vector right here is pointing to -2 comma 3, which is my original point A. And if I plug in 1, watch this. If I plug in 1, -2 plus 5 times 1, comma 3 plus 3 times 1, here I'm going to get -2 plus 5 is 3, and 3 plus 3 is 6. I'm going to get my value of B. And if I was to plug in a number like half, then I would get the point that is right between the two. And if I were to get 2 or 3 or 5, or it doesn't really matter what point I plug in for t, they are all going to lead me to some point along this line. And so for that reason, this right here is the parametrization of this line. Now, if I wanted to make this a line segment, which means that I was only looking for this point right here, I was only searching for the points between A and B, then I could go ahead and specify, well, that is just on the interval zero is less than or equal to t, and t is less than or equal to 1. Because like I said before, when t is equal to 0, I get that point, and when t is equal to 1, I get point B. So that is how to find the parametrization of a line or of a line segment by using vectors that basically point to any point on this pink line.